All right, hello everyone. Welcome to our today's colloquium. It is my great pleasure to introduce our speaker today, Paul McEuen from University of Cornell. Paul has received his undergraduate degree from University of Oklahoma in engineering physics. Further, his PhD from Yale University in applied physics. He completed his postdoctoral training at MIT, after which he started his group at the University of California in Berkeley. He has moved his group in 2001 to Cornell, where he is until now and currently is the Goldwin-Smith Professor of Physics. He's one of the world experts on carbon nanotubes and a member of National Academy of Sciences. He has received a number of awards. Moreover, I would like to mention, he's also an accomplished and published author of a science fiction novel that is actually situated in academic environment. So if I were you, I would be very careful what kind of questions you ask at the end of this colloquia or at the cheese reception, since you might see yourself in the next novel. So with that being said, please.
Well, thank you very much. Yeah, if you want to, feel free to get on your phones, go on Amazon, buy the book right now. That's okay. We will wait for you. Go ahead. Spiral. Yeah. Just type in that name and you'll get there. I've only got one so far. So in fact, this talk is basically my attempt to do what the lead character in that book did, which is to build small robots. And so I'll be telling you that story as we go along. So the title of our story today is The Future of Small. Where is small going? What's going to happen? And I'll start our story. If you're a physicist and you're talking small, you got to go back to Richard Feynman, who made this very, very interesting speech back in 1959, where he said, you really can just take things and make them small, and that's pretty interesting. At that time, everybody thought about making things big. You wanted to go to the moon, you build big airplanes. It was all about big. But Feynman, being Feynman, said, no, small, that's pretty cool too. Now, of course, this wasn't in a vacuum. At that time, computing was really starting to kick up. After the war, Silicon Valley was starting to take root. So in many ways, Feynman was just reporting on what was going on and then projecting forward based on how things should go. And the first thing he said is you should just miniaturize like information and computing. And if you do that, that'll be awesome, because there's no reason, it has no essential scale. You might as well make it small. You can put a lot of stuff in there. And when we're thinking about the impact of that, I like to use this. All right, so that's the story of the computer. We're the frog, this is the fly, I would say, these days. So we just do what this thing tells us to do. That's the way that, it's a virus that's taken over us. But it's a pretty cool one. It's got lots of pretty pictures going on it all the time. Keeps us entertained and happy as we go about our day. Feynman was right. Making things small worked, and information and computing, if you make them small, you get this unbelievable technology that has, in the case of an integrated circuit, something like the complexity of the city of Manhattan realized in something you can carry around in your hand. And that's basically what's going on here. And furthermore, the processing speeds are such that basically a lifetime goes on every second of the residents of this fake city of Manhattan inside of this phone. There's an enormous amount happening that you got just by making things small. Things that work just the normal way that they would when they were big. You just shrink them and you get this incredible processing power in small packages. Really amazing. And this game is not over. There's still lots of effort going on, and for example, pushing these kinds of electronic materials down to the ultimate limits is a subject that has gained a lot of attention recently. For example, there are all these two-dimensional materials, atomically thin sheets of materials that are quite stable. Graphene being there's the subway, I guess. Okay, I'm getting used to it.
That's an earthquake.
That one's an earthquake. All right, good to know. Things like graphene, silicon dioxide, boron nitride, molybdenum bisulfide. There's a whole family of new two-dimensional semiconductors metals and insulators that people are playing around with, including people in my group, just pushing this process to the ultimate limit. Can we make the world's smallest electronic information processing devices? And you know, my group continues to work on this a little bit. This is a blatant advertisement for a paper that we had that came out in Science a little while ago, advertising things for my postdocs Longzhu and Lei Wang. And I have to do this because I'm not going to talk anymore about their work. So let's move on. So this is all interesting and we're having fun. But you know, if you read the trades and you start looking around, you'll see stories like the semiconductor industry will soon abandon its pursuit of Moore's law. Moore's law is dead. Now what? Now what? Basically, Feynman's program is over. We've made things about as small as we can do without the problems that arise from making things small kill us. The heat dissipation problem hasn't been solved. The layers are so thin that things tunnel through them when they're not supposed to, et cetera, et cetera. We've come off of Moore's law for a few years now and are not following that path anymore. So what do we do? You know, is that the end of the game? Is small almost over? Well, I hope not. But it's okay, because if you study this view graph, you'll notice that there's an empty space there. So something good must be about to happen. Plus it's number 1. You don't have a number 1 unless there's a number 2. And number 2 is something else that Feynman said in this talk back in the 1950s. He said, you should also miniaturize machines. There's nothing that says you can't make small things that do stuff. And by machines here, I don't mean computing. So anything that just moves informations and electrons around, we'll call that computing. And anything that tends to move matter around, we'll call that machines. Okay? And he said, miniaturized machines, and basically not much has happened on that front in the last 50 years, unlike in electronics. Some has happened, and it's speeding up. You know, we have drones and what have you. Getting machines smaller is starting to become a priority. But for the better part of that last 50, 60 years, we basically have ignored the challenge of building small machines. And you might say, well, why do you even want small machines? What are they good for? Information is scale invariant, so you might as well make it small. But machines, maybe, you know, we want big machines because we want them to carry us around and stuff like that. Maybe that's why we haven't made them. But, you know, just to take a little bit of inspiration from biology, you know, run a little bit of this movie, which is a cartoonized version of what goes on inside of a cell. And what biology does is uses an incredible array of really awesome small machines to do all kinds of amazing stuff, carry around big giant bags of something or another. It's incredible. It's actually much more complicated and noisy and ugly than it looks like here, but you get the basic idea. We are built out of small machines doing all kinds of incredible functions. And so if you can build a technology like that, you could build something with the sophistication and complexity of us. We've already built things with the sophistication and complexity of our brains, but we haven't built anything remotely like us. You know, what this makes me think of is something Buzz Aldrin said on the cover of MIT's Technology Review. He said, "You promised me nano-submarines, instead I got Facebook." And actually, he didn't say that. This is very bad Photoshop, as you might be able to tell from the little black box. He said it was something about space colonies. But you get the idea. This information technology is cool, but it's not half as cool as what we will be able to do if we can make tiny machines. So that's the pitch. We really should do this. This would be great fun. Let's miniaturize machines. That's the subject of the rest of the talk, is how might one go about that? And that gets us to the actual introductory slide, the real one that has all the names and the pictures and what have you. And in fact, I've changed the name of the talk. This is really about building the small machines, which I'll use the word nano-submarine as a substitute for that. And in particular, we're not going to really get there, so to manage your expectations, we're only going to be building the parts for the nano-submarine, the bits and pieces that will be used to construct these small-scale machines. And I'll tell you how we're doing it and how it's going. And this is a big group of folks, including a lot of really great students and postdocs, but there's also a number of faculty involved at Cornell in this process as well. In particular, Itai Cohen, Ji-Woong Park, who's now at Chicago, David Muller, and Al Molnar were very big players. I should also say one other thing. We're calling this the nano submarine, but it's really not going to be a nano-sized submarine. That would be super hard to do. It's going to be a micro-sized submarine, but with nano-sized parts. So the parts are nano, not the submarine. Micro-submarine just doesn't sound as cool. And usually people, if they say a micro-submarine, it would be millimeter scale. So we have to keep playing the game. Okay. So, I mean... That's correct. Yeah, I didn't tell you what was in front of nano, right? You know, nano megameters or something. So let's say you take this a little bit seriously and you really decide, well, okay, I want to make these things. You know, what might you want them to do? So you want to build some cell. Let's say we're going to do something at the size of a cell, because that's sort of the smallest complex system in a biological unit. What would we want to be able to do? Well, it needs to exist. It needs to have some 3D structure. You need to make things that actuate, things that can move, that can cause motion or grab something or what have you. You're probably going to want this thing to do some sensing. It needs to record feel what's going on in its environment in one way or another. It needs to be able to communicate that information back out to you in the outside world. And also, you should be able to communicate information and power to it to help it do its job. So you have to establish a communication flow in and out. And you may also want some computation and memory on board to do some processing or to remember some things or what have you. So this is the kind of elements that you would like to have inside of your nano submarine. So it sounds like a lot, 5, but that's a pretty big number. What are we going to do about that? Well, I'll quote Picasso, who said, "Good artists copy, great artists steal." So our goal is to steal, and Picasso did that a lot. He stole from Braque, for example, quite a bit. They stole from each other. But we would like to steal. And there's a couple of different ways you could go about stealing. You could, for example, if you're a synthetic biologist, you're stealing from biology. You're just ripping off that technology straight away, hack it. I don't have to really know how to make it work. I just have to know how to program in it, and off it goes. Okay? But there's another technology that you can also steal from that we've already talked about, which is, for lack of a better word, I'll call it silicon, transistor, integrated circuits, whatever you want to call it. There's this unbelievable materials technology for making unbelievably complex systems that, again, give you things like your cell phone. So maybe we can steal a lot of this technology for our purposes here. And so that's what we're going to do here. We're not going to be like the synthetic biologist and steal from biology, which is a really cool thing to do and in many ways will happen faster than what I'm describing. But this gets you all kinds of other fun bits that we'll see as we go along. Okay. And the first thing is, for free, you basically get these 3. Okay, you've got computation and memory. That's what it's all about. Communication, we've also got that. There's a lot of optics and RF and every other kind of photon you can think of type of communication systems for these devices. There are all kinds of sensors on board that you can think about: magnetic, electric, chemical. Any kind of sensor that anybody builds almost invariably gets converted to electrical signal. So you can slap it on top of this technology. So these 3 are in a certain sense done. They're done for you. And that just really leaves the other 2. But before we get to the other 2, I just want to talk about these 3. So just going after some things in these 3 and applying them to this problem of making small active systems, already there's an enormous amount of work to be done that's very low-hanging fruit. So in particular, I would like to point out this idea of the smartphone and use it as motivation. So what is so great about a smartphone, in addition to all of its computing power, is it basically solved the communication problem for you. This thing knows how to talk to the outside world and listen to the outside world, and then has a platform on which you can do anything else. You can put apps on it, you can do all kinds of stuff, but they just solved the I/O problem once, and then you get to carry this around, that everybody just gets to develop stuff on here. If you want to make a camera that can communicate with the internet, all you have to do is make the camera. You don't have to make the communication system. So this idea of having a smartphone is a very powerful one. It is modularly separating out the communication part of the problem from everything else. And so there's human smartphones, and in fact there are also molecular smartphones. You might know them by a different name. You call them a fluorophore. So fluorophores have taken over biology in many ways and have been incredibly effective ways of reporting back what's happening at the nanoscale in a biological system. And how does this work? Well, it's this little molecule. You shoot light at it, so that's the input information or power. It then shoots light back out. It communicates back to you. And in between that, something happened where the fluorescence, the amount of light coming out, was affected by the pH of the surrounding environment, whether a neuron fired, if it's an electrical signal, or maybe it's just reporting back its position. Its only goal is to just, light up and say, I'm here at this location. So molecular smartphones exist, human smartphones exist, but what about in between? And I should say, this is sort of the generic story of nano. The story of nano is we know how to do things at big scales. The chemist figured out how to do things at the molecular scale, and we want to fit in the space between them and learn how to engineer at that intermediate scale. That was the case in more or less always the story of nano. Okay, so what would this smartphone for cells look like? Well, we want it to be cellular size, so we need it to be 100 microns or less. We needed to communicate, and we are going to actually adopt the molecular version of this. We're going to use light to get information in and out of our smartphone. So all we have to do is take existing technologies for making semiconductor devices and put them together. So we have on this wafer here, this is something that was made by Alejandro, my student, at the CNF, Cornell Nanofabrication Facility, where he went in and just fabricated a bunch of standard electronics. This thing has things like photovoltaics on it. It has things like LEDs, this thing that was lighting up and appears to have stopped. It has a transistor, et cetera, et cetera. This is very basic electronics. In fact, the only thing that's a bit interesting about this is the fact that this thing here, this LED, is integrated with standard silicon electronics. The LED is made out of gallium arsenide, actually a gallium arsenide heterostructure, and Alejandro had to work out some techniques for taking a LED made on a gallium arsenide heterostructure, transferring it over, and integrating it with silicon in an aligned way. And he worked that out. And actually, a lot of the tricks that he learned, that he used to work that out, were things that were learned in the 2D materials world for learning how to get a single graphene sheet off of a piece of copper and transfer it onto a silicon wafer or something. So a generation of hard condensed matter physicists got used to doing soft matter stuff, like putting a PMMA layer on something, peeling it off, floating it off on the surface of the water, scooping it out, et cetera, et cetera. So that marriage of hard and soft is made it much easier to integrate electronic bits that come from very different sources and put them on a single chip. So as a result, we can mix LEDs, photovoltaics, so that's light in can power things, the LED can report back out, and then standard electronics comes along for free if you just do standard processing. And then the goal is this is then made, and then we're going to set them free in a little bit. Okay, so a little more detail, and here's another picture of one of those. Each one of these, they even kind of look like old style cell phones a little bit. This one, I can't remember the exact dimension. This is about 100 microns, maybe 50 microns that way. They're not particularly small. This thing you see here, this is a bank of photovoltaics that you shine light on it to power it. And what this particular one does is its goal in life is to measure the voltage between that probe and report it back out in the intensity of light coming out of the LED. So it's a simple circuit that's all it does. It measures the local voltage. And there's the thing blinking as we change the voltage going from here to here. So this one's still sitting on the chip, and we brought in probes to apply the voltage across it. But when we're going to set this thing free, it's going to measure whatever electric field is in its environment. Okay? So that all works. And one question you can ask is like, how sensitive is it? And this just gives you a sense. So we're putting in a 50 millivolt signal into the gate electrodes and then measuring the output light coming out of the device, how it's blinking. And this is in milliseconds. So each period of this oscillation is about 1 millisecond. It's a kilohertz sine wave. And if you look at the noise of this, it's got sort of millivolt noise in a 10 kilohertz bandwidth, something like that. So it's per root hertz, it's in the tens to hundreds of microvolts noise level, which for many things is more than enough. And I'll mention, just like a smartphone, the one I just described was this one here is nothing more than a voltmeter. You can make other things that have thermometers on board so they can measure temperature. This one's a bubbler. What do I mean when I say a bubbler? These are all going to be living in liquid. And one thing you can do in water, if you apply a large voltage between two electrodes, it makes hydrogen and oxygen in the forms of bubbles. It splits water and creates bubbles. So this one, you just shine light on it and it will create bubbles of hydrogen and oxygen to control pH and what have you. And again, this is all circa 1970s circuit design. And then once you've got them tested and built, you encapsulate them in something to protect them from their outside environment, except open up holes where the electrodes are. That's what this sort of unusual optical contrast is. We have SU8 on top of these devices, and then the electrodes exposed. And then you etch out the substrate underneath them. That's what's happened here. You've etched out the substrate underneath them. They're almost floating, but they're held in place with little tabs, just like when you made a model when you were a kid. They would have the model pieces with little tabs that you would snap out to get them free. Here's a few that have kind of popped loose. Okay? So these are off and ready to go. And we're just starting to test these in a variety of environments. So this is, you set them free and then they float around in solution just like little bits of dust. It's hard to see because they're small, but there's little, he shook the container, those little bits of silver fleck floating around, those are little electronic devices. You can deposit them, for example, this is one sitting on a bunch on some cells, and then if you apply, for example, in this case, just to test it, we applied a voltage across the solution, and we can measure the output, the change in the voltage in the solution, again with a sort of millivolt type voltage resolution. So you can make these things. It's not particularly hard to do, but it's a lot of fun, and we're having a great time doing it. At this point, you might ask, well, why? Why do you must have some actual reason for wanting to do this. And the main reason is we're just having fun and we're curious, but you have to get money, and so you have to tell a story. So I'll tell you one story that gets us money out of the NIH, out of the Brain Initiative, which is, if you look at how people do neural recording now, it's pretty crude. It's getting better, but it's still pretty crude. Roughly speaking, you take an ice pick and you jam it into someone's head and hope that they don't die, right? And then there's some wires come out. Now the ice picks are more sophisticated. They now have lots of electrodes on them that go back out to a connector. But usually, or at least often, there's a wire connection from the brain out to the circuitry, and then there's a bank of amplifiers that they all plug into and what have you. And one of the big drives in neuroscience now is to move as much of that technology off the rack and back up toward the head. A lot of the rack stuff is being replaced by integrated circuits that are in the connector, et cetera, et cetera. If you have John Rogers give you a talk, he'll show you his flexible electronics that are made to just lay on the dermis of the brain to record stuff out. So there's a lot of integration to move that technology toward the head. Having said that, most of it still involves wires connecting you to the outside world at the end of the day. And a number of groups are trying to think of various ways to get rid of those wires, to have a wireless connection. And we're one of those groups that are thinking about that. And our idea is very simple. We take this thing that I was describing to you before, and you would just stick it into the brain, and it's a wireless thing. And we're going to use light in and light out to get the signals in and out of the brain. Now you might say, well, I got news for you, Paul. You can't see through your head. That doesn't work. But you can sort of see through your head. If you have a laser pointer that's red and you put it to your hand, you can see a little bit of light come out the backside. In the infrared, there's a decent amount of tissue penetration that you can get. And in fact, a lot of the light scattering is elastic, the light scattering in the brain. So you can actually couple in a lot of light. In tests in animals, they will put in many suns worth of illumination inside of the head of the animal under test. So its whole head is glowing with diffuse light, many suns in intensity, and it doesn't fry the brain, at least not too fast. So you could put devices in there to suck solar energy out and power themselves. And if they blink, they could send information back out that you could detect, maybe not so much with ray optics, but at least you would get a faint blinking out. And so that brings up one of the features of this device that we designed. You may look at it, you can't really see too much, but it looks a lot more complicated than the circuit I showed you before, and in fact it is. And this is a circuit that was designed by my collaborator Al Molnar that has a whole bunch of pieces on it, but whose job it is very simple. This is a device that again is a few hundred microns wide, and this one's about 50 microns across. It's supposed to measure the voltage between that pad and that pad. It gets its power from a photovoltaic / LED that we glued onto the middle of it, just like the ones I was showing you before. So you shine light on it. Most of the time it's sucking up energy, and then once every kilohertz, it turns around and reverses the biases and biases the p-n junction the other way and puts out light. And it blinks not once but twice per cycle. And the reason it blinks twice is it blinks once to tell you, I'm starting to tell you something, and then it blinks a second time to tell you the thing. And the information is encoded in the distance in time between those two pulses. So the pulse distance tells you the voltage. And it's encoded in time instead of in amplitude, because then you don't have to measure the amplitude accurately. It's sort of like FM or something. So this circuit is set to do all that stuff. So the circuit design has to do all those things that I just described to you in words. And then we don't build this one ourselves. It's designed, it's sent off to a foundry somewhere in, I don't know where it is, I assume it's in Taiwan, and then it comes back to us, and then we set the devices free after that. So we outsource all the complexity. So the silicon in this, I forget the line width, but it's on the order of 200 nanometers, the technology. And it's not cheap, but it's not that expensive. And in fact, once you've got the masks built, subsequent wafers are cheaper still. And plus you get thousands of them or millions of them at a time. Okay, so does this work? So we've started to test this out. We haven't stuck this in a brain yet, but we've done the next best thing is we've taken 2 wires off of it and stuck it in a worm, and stuck it into a neuron that's firing in a worm, or a nerve that's firing in a worm, and don't have any other wires connected to this. We just shine light on it and watch it blink. And this is the output, so this is the intensity of light coming out as a function of time. This is the background noise, and then there's a bunch of spikes that happen over the course of seconds. And if you zoom in on that, you see that there's a bunch of little spikes, and again, the separation between those spikes encodes the voltage measured at that moment in time, and it repeats this at 10 kilohertz, which is fast enough for any neural signal that you care about. And this is the reconstructed, you take that time information, convert it back to voltage, this is the reconstructed neural pulse that happened, again, measured just by shining light on this thing and watching it blink. And we also did measurements where we replaced this with the standard setup, and this was at least as good, maybe even a little better than the standard rack of electronics. And it gives you all sorts of things for free. It's happy to be very fast because there's no big wires with lots of capacitance, et cetera, et cetera. It's really kind of a fun platform just to move the conversion of the signal to light as early as possible in the process. It does lots of fun things for you. So, this just goes to show, just by ripping off standard technology, you can do a lot here. And honestly, I think a lot of these things will be very economically relevant in the future. You're going to have smart dust that you can spread around anywhere that will communicate with anything. You'll put it in your food to see if it's spoiled, et cetera, et cetera. You'll see a lot of this kind of technology everywhere. And I'm not saying that we're pioneering all of that. There's a lot of groups coming from higher scales down, but this will be a theme that you'll see over and over. Having said that, we've completely avoided the first two. This is a 2D technology. The fabrication processes for semiconductor devices is a planar technology. Invariably, I'm going to probably want this thing to be a 3D object, and it's going to want to actuate. It's got to fold itself up into a 3D shape maybe, and it's got to move around, and it may have to swim, and it may have to crawl inside your brain, etc. For example, in the neuron case, you may want this thing to have electrodes that aren't passive, but can reach out and push to get a better neural signal. It's very important, the detailed connection between the electrode and the neuron in terms of how much signal you get. And also you may want to get it in there, you may want to just inject it right through the skull and then have it turn into a worm and crawl its way into your brain. And if that freaks you out, I know, me too, but it's exciting as well. I don't know, I'm excited. And it's really interesting, there's all sorts of other constraints from the biology side that we're beginning to learn about from our colleagues. For example, if you can make these cell phones smaller than about 30 microns or so in width, if they're little needles that are less than that in width, they don't seem to create a lot of negative response, meaning you don't get scarring and tissue damage. It doesn't set off the brain doesn't go, whoa, something bad's going on here. So there are also lots of geometric constraints that will be set by biology as we actually try to use this for something. Anyway, but how are we going to do this? How are we going to deal with these other issues? And again, if we go back to biology, biology has solved this problem in a pretty insanely cool way. It takes an information strand, or basically a bunch of coded information, writes that into a linear polymer that, unlike this model here, has a lot of information encoded along its length. That thing folds up into a 3D structure that is a machine that does stuff in response to other signals, and it creates all this. Okay. Well, that sounds all well and good, but boy, I have no idea how to do that. I just absolutely no idea how to do that. But there is something that's sort of like that, but it's also sort of like everything I've told you so far. And that is this. So you can take a sheet of paper. You can define a set of lines on the paper, like I've shown here. And those set of lines are actually encoding a 3D shape, that if you will fold along those lines in the right way, you will get a particular 3D shape. And I think in this case, it's utterly and completely obvious what that 3D shape is, right? Yes. Of course, yes, it's an elephant. Yep. And you may say, I don't believe you. There's no way that this is an encoding of that. But in fact it is, and this artist here made this nice movie that proves the point. Here goes the folding. Off we go. And there it is. That's pretty cool, right? And you know, it's very inspirational. I'm sorry?
Was that movie made by unfolding as a thing backwards?
Made by what?
Was that movie actually it being unfolded, just played backwards?
You know, that's a good question. I don't know. I think the answer, actually I have no idea. I should find out. I'm sure it's on the web, but it's obviously stop motion. But it's inspirational in the sense that it tells you what we want to do. We want to start from a planar system and encode some information in the planar system and have that realized into a 3D shape. And for free, of course, you get actuation because this thing was moving the whole way. And so you could have other things happen to cause the trunk to move or anything you wanted along the way. But we want it to work sort of like this. We want it to fold up, and we want it to be magic. We don't want to have external hands in there doing it. So this is our inspiration. And you know, you may say this is a joke. You know, this is origami. This is art. What does this have to do with technology? And I'll just say that there's an enormous, kind of very interesting little mini revolution going on now, where these kinds of ideas of this sort of thin plate geometry is explicitly in the context of origami, but also more generally, is being used to engineer all kinds of other cool structures of many different sorts. At architectural scales, it's being used to make doors and walls that can be moved around. Whole buildings. There's a building in New York City right now that's being made that I think does, that folds and unfolds. You can make things that do all kinds of fun stuff that can crawl and what have you by changing their folding shape. Robert Wood, for example, is getting very good at making pop-up book flying creatures. That's a neat technology. One early application was if you want to make deployable stuff into space, you need to have it in a small package. You get your origami artist, Robert Lang, to tell you how to fold it up, ship it to space, and have it unfold. And at the level of small stuff, this is a thin polymer sheet that actually has multiple layers that is designed when you expose it to the right environment. Things swell in such a way that causes it to fold up into a very tiny little bird. I forgot how big this is, but it's pretty darn small. So this approach, 2D to 3D, is really catching on. I've seen all kinds of versions of it, including ones that, you know, you can basically take a 2D printer or a regular printer that defines certain lines in a system, and in fact, if you have bilayer paper, it puts water on the paper that causes the top layer to contract in a certain way that will have it, as it comes out of the printer, it folds itself up. It really is a technology. And another fun thing about it is that it does work at all these different scales. And just to you know, in echoes of Moore's law, these paper arts scale. This mechanical approach, if it works at the macro scale, if you shrink all the parts down, including the origami artist, it will work at the material level more or less the same way. This energies all just scale as volumes, everything scales down. Okay. Now, like any good scaling law, not everything works. For example, gravity doesn't scale in the same way, so gravitational forces are different. Adhesion forces, sticky forces, don't scale properly either. And in fact, at small sizes, adhesion forces take over in normal systems. Everything sticks to everything. The world is flypaper when you're at the smallest scales. And for that one, we will use the same solution that biology used, which is you put everything in water, and then you have other, you know, water can basically help mediate the surface forces. Water plus surfactants plus all the other tricks that the soft matter physicists have given us will allow us to control those surface forces and make things stick or not stick as we wish. But anyway, it's a cool idea. Okay, so the question is, can we, using the same set of technologies, push ourselves and solve these two problems using this technology and those ideas? And that's the goal. And by the way, that brings us back to these 2D materials, because if you're thinking about doing things out of paper, and I told you you have to shrink the paper down, well, let's go ahead and ask how far can you shrink the paper? So what's the ultimate limit? The ultimate limit would be to shrink the paper down to some 1 atom thick layer or 2 atom thick layer, something very thin. And in fact, this is how my group got into this whole game, is just for the fun of it, a few years back, we decided to try to use paper arts with these atomically thin materials. And if you go online, and we went to a Kirigami website. Kirigami means you can cut the paper, because it turns out that's even easier than folding the paper. You just cut it and stretch it. The website, if you go to the Kirigami website, they'll say if you're a kindergarten class, what you should learn how to do is make this device here. You just make these series of cuts in the paper. You pull on the paper and you turn it from something that is inextensible to something that stretches really easily by the thing buckling out of the plane. So 2D going to 3D, in this case, gives you a soft spring. And so we said, okay, we can build that. So we basically built this out of graphene a few years ago. And this is what that looks like. So this is a single graphene sheet that's been cut to look a lot like that. And then there's a probe that's grabbed a hold of a pad that's pulling on it, and off you go. You can see it stretches. And it's pretty amazing. I should say that it's amazing in many ways, not the least of which you can do this for hundreds or even thousands of times. And if you never pull it too far, it just keeps going back. It's quite reversible. The carbon-carbon bonds don't break. They're very strong and stable, even though it's a 1 atom thick material. This stuff is very tough. It can handle a wide range of pHs. It can handle a wide range of temperatures. It's really a robust material compared to sort of organic or biological versions of the same. And honestly, that's one of the reasons we like these hard technologies, these silicon and other thin film-based materials. They access chemistries that life never figured out how to. They have bonds that are extraordinarily strong and aren't going anywhere. So they tend to be much more robust than any biological counterpart. Okay, so we made these Kirigami devices, but we want something that folds not by using a probe to pull it. We want it to self-fold like that elephant did. So you have to make some sort of actuator that will do that. Plus, we don't just want to do Kirigami, we want to do origami. We want to have panels and folding and stuff. And so that leads us to this picture, which is sort of the model for where we're headed now. And telling you this little bit of story will be the last part of the talk, is what we're going to do is break our system up into what we call panels, which are the green things up in this picture here, and these little blue things up here. These panels can be anything. They can be just passive objects. They can be electronics. They can be lasers. They can be whatever you can fabricate. They sit on top of some little thin layers, which in this case is a layer of graphene and a layer of glass. They're very thin. Those combine into a structure like that in principle should be able to fold up on its own. And it must work because there's some little movie running over here in the corner of about a 10 micron on a side little set of pyramids that are folding up. Okay. So the folding up is somehow associated with the stuff you can't see that's in the joints, which is this very thin layer of graphene and glass. And so what is that? Well, that is something that, you know, again, with the idea of stealing, we steal from our mechanical engineering friends. If you ask them how to make something bend, if you want to make an actuator, they'll say use a bimorph. And a bimorph is nothing more than two layers of material that you put on top of each other, and then you make one of the materials either contract or expand, and it will cause the whole thing to bend to deal with that contraction or expansion. Okay? Very simple. You can find this in, you know, I don't know how it goes back, hundreds, probably thousands of years. And furthermore, it's been an approach that has been adopted by many people trying to make little foldy structures at larger scales for quite some time. So the only innovation we were bringing to the game was to try to take this down to a smaller scale. So there's nothing new here except for the layers are thinner than they'd ever been before. So we're using, instead of 100 nanometer thick sheets or, you know, 1/10 of a millimeter sheets, we're going to use a couple of nanometer thick sheets to make this go. And the work, by the way, has been led by this guy over here, Mark McEuen, who is a Kavli postdoctoral fellow in my group. And I want to say one quick thing about that as an advertisement. I'm the director of the Kavli Institute at Cornell for Nanoscale Science. And one thing we do is we support a Kavli postdoctoral fellow program that funds people like Mark McEuen. That's Fred Kavli there, standing next to our institute name. And if you like the work that you're hearing here and you're about to graduate and you think you might want a postdoc, check out the next announcement for our KIC postdoctoral fellows. With that advertisement, I return you to our regular program. Okay, we were going to make this bimorph. The bimorph in question has graphene and 2 nanometers thick of glass. You may ask, how do you make 2 nanometers of glass? You go into the Cornell nanofabrication facility and there's a big machine and you put your sample in it and you push a button and you wait and then you take it out and it's done. Okay. That machine is what's called atomic layer deposition. It's a now standard growth technique that basically grows half layer by half layer in a controlled manner, and it's sort of a poor person's MBE or something like that that makes very thin layers quite well. And so you can grow 2 nanometers of glass that is basically has reasonable structural integrity. Also 2 nanometers of lots of other things as well. So you can use lots of different materials. And in fact, in this problem, the graphene is the boring, stupid material. It's just there to be a structural material. And the glass is going to be the smart material. It's going to be the one that does something. In fact, this thing you can barely see, which you can barely see it because it's a sheet of graphene with a little bit of glass on it. Not a lot of optical contrast there. This is an optical microscope. But if you heat it up, if you shoot a laser at it, for example, and heat it up, it will curl up. That's that bending. It's bending so much that it turns into a spiral. And so this one is doing it just based on the differential thermal contraction of the glass with respect to the graphene. So it goes from that to that, which makes it curl up.
This is a super technical question.
Yep.
In order to do it, don't you have to elevate the temperature to get it to 1,000?
Yeah, so it's all done that, you know, yeah, so that process, so we actually do all that and then put the graphene on top, actually. But yeah, the ALD process is a modestly, I don't remember what temperature it is, but it's a modest temperature process. But it's fine. This is, all the processes to make these things are consistent with, you know.
But does it come out in the stress state then?
Oh, you put your finger on a very important point. Learning how to control the inherent stresses in these layers is a big challenge. And you have to get the recipe right, and it's a lot of fidgeting and what have you. So most of them come out with a little bit of residual stress, so they come out bent a little bit. And so you work real hard to try to get control of that. And our control is not terrible, but not good at this point. But, you know, it's one of those things that until you dedicate an ALD system for just this and really dial in the parameters, in a research environment, you're never going to do a great job. But I'm confident that once you decide what you really want, you can throw money at it and get it right. Yeah, because one other point I should make, the stresses in the film that the amount of contraction or expansion we're using to make our things actuate is like 10 to the minus 3 or something. Very tiny strains. And that's enough to cause the actuation because they're so thin that 10 to the minus 3 times a nanometer turns into a micron radius of curvature. Okay, so I said you could do it with thermal. Actually, we have a better version. The version that I showed you before with the movie flowing up here actually involves using another trick, which is to change the pH. And the story of that is written inside this little box here. I'll just mention it briefly. There's a gorilla in there staring at a piece of glass. That's Corning's Gorilla Glass. If you're in upstate New York, you know all about Corning and you know all about Gorilla Glass. That's the stuff on your phone. It is glass that's under stress, so that when you scratch it, it kind of self-heals. It kind of closes up that gap right away. And the way they do that is they basically heat the glass up to a high temperature and put potassium in it, and potassium in it, and that substitutes for the sodium, which puts the glass under stress. There's a lower temperature version of that happens with pH, that if you change the pH of glass, it is well known to the glass scientists in the world that at some point hydronium will substitute for the sodium, and the hydronium is bigger than the sodium and will put the glass under stress. So as a function of pH, you'll also see a transition. And that's in fact how all these were made to fold. Both this little one, the movie I showed you, and this is the image of a bunch of slightly more complicated things that we fold, little cubes, a book that closed, and even the little hinges closed for some reason. These are the paper models. This is the ones we made, and this is them in their flat state. And so we're starting to get better at this all the time. I'm sorry? Yeah, the elephant brings up all kinds of other problems, as you might imagine, not the least of which is, maybe I'll use that as a segue. This, at least the way we're doing it here, everything fires at once. We tell it to fold, all the hinges fold at once. Obviously, to make an elephant or anything slightly more complicated and interesting, you need to have control over the folding times. You need to fold this, then you need to fold that, etc. And if you want to make an actuator, you don't want the whole thing to do this. You may just want this arm to do this. So you want to get control over the folding process.
Sorry, they do unfold also?
Yes. If you change the pH back, this will unfold. It's a reversible transition. You'll see more of that in just a second. We're moving into the last leg of our story. So this sounds okay, but there is something wrong here. That I'm a physicist, and this is pH. This is chemistry, right? pH. I can't even remember the direction of that, right? Is pH big? Is that more acidic or basic, or I don't know. It's confusing. I hate it. It's terrible. Hydronium. What is that? Okay. And there's a bigger problem, is that we want to do these, but if we use pH, we've lost all of these. Right? If we're using pH to drive these transitions, there's a sense in which that doesn't communicate with all the electronics that we have. Maybe we would use our bubbler to make hydrogen and cause it, but that sounds terrible. If you really want this thing to work properly and you want it to communicate with this part of your robot, you've got to do it electrically. You cannot do this with pH. You need your muscles to work with voltages, like any self-respecting physicist would want them to work. Well, it turns out that that's easy enough to do. And this is the last thing I'll tell you about, is you can do almost the same thing. There's the graphene sheet. This layer here, the glass has been replaced by platinum, again, made in the ALD machine. Now, platinum, as you might know, also likes to soak up hydrogen. However, the interesting thing about it is if you change the voltage on the platinum relative to the surrounding electrolyte, it may soak up the hydrogen or let the hydrogen go. So it is a voltage-controlled soaking up of hydrogen, which leads to a strain in the platinum field, the platinum layer of about 10 to the minus 3. So all I have to do is apply a voltage to this thing, and the ions will move in and out, and off it goes. By the way, one nice thing, you could try to make this with a macroscopic system, and it would never work, because if the platinum was very thick, it would take forever for the hydrogen to diffuse in. But because it's just a couple of nanometers thick, in this case about 5 nanometers, the diffusion time is faster than we can tell. So it's sort of milliseconds or something like that. So it's fast enough. And so does that work? And the answer is yes. So this is one of these bimorphs, platinum and graphene. You apply voltages to it of any sort you want, and the thing will tighten up to sort of a micron radius of curvature, and then go back out to more or less a relatively flat state, and anywhere in between. Now there's a second question you might ask is, what's the voltage being used to actuate this? How big of this voltage do I have to apply? And that's shown in this graph here. This is the curvature of this thing as a function of the voltage applied relative to the surrounding electrolyte. And you'll see that it goes from a one state to the other state, and it does it in about 100 millivolts or so. So 100 millivolts applied can cause something to go from basically flat to a less than a micron radius of curvature. That's a pretty good robot muscle for a microbot. And I don't know of anything else that works that does this. This is, as far as I know, the best muscle that you could make for this kind of microbot that I know about. So we're very excited, and again, we're happy to be using voltages instead of silly pH. So it makes us very happy. And the other thing is you have to work at these low voltages if you're in an electrolyte, because if you go above a volt or two, it'll start making bubbles and all sorts of bad things will happen. Okay. And so, you know, if you have a sort of a complex and you need people to worship you, you can make millions of these things doing this. This also begins to show you a couple of other things. First, the residual strains. You'll notice some of these are a little more bent than others. But it also says, you know, you could also probably make microfluidic pumps and things like this with these that work very easily. You could integrate them in a very simple way. This is just a couple layers of ALD and off you go. So we're pretty excited about this for doing all kinds of things. And so, you know, we really feel like we're starting to have the toolkit to build our little bots. And just to close out, I'll tell you where we're going, which is completely obvious. Is you know, we have these electronic things, and now we have these electrically actuated muscles. Now we just want to start putting the pieces together. And you know, the most obvious thing to do is instead of having to have a wire to drive the voltage, we, for example, could. I think I have a slide on this. No, I don't. We could have a photovoltaic. You shine light on it. It generates a voltage. The voltage causes the muscle to move, et cetera, et cetera. And in fact, that's what this last little thing is. Basically, these are these platinum graphene bimorphs. This is a photovoltaic. This is another photovoltaic. So you'll shoot a laser at that one, and then these legs will actuate. You'll shoot a laser at that one, and these legs will actuate. You make friends with David Greer, and he can put in some arbitrary light pattern on your sample and cause your robot to do whatever you want. Light information will get immediately transferred into mechanical actuation. So we're super excited about this. The only problem is that they're super excited about it too. That's again Mark. The only problem is they still haven't worked yet, but soon. If you ask me back in a couple of years, I'm sure they'll be running along. And you know, again, to set the size scale, the basic rule for the group is everything we do, you have to be able to inject it. Okay, if you can't inject it, we don't care about it. So we're totally into injectable machines and what have you. And we think this is pretty cool, and we're very excited, and we're you know, kind of hoping that we can take Buzz Aldrin, who's not looking so happy, and you know, cheer him up just a little bit. So with that, I will end, and thank you for your attention.
Question?
What about work and energy?
Yeah, this is a really good question. There's another. I didn't talk about this because we haven't done enough work yet. But one of the rules for ourselves on this is these machines need to be reasonably efficient. What does reasonably efficient mean? For us, you know, at least at this point, it means anything should be at least 10% efficient, any particular step. So maybe the whole robot might be 1% or something. So we're not allowed to throw away huge amounts of energy. And in fact, most tricks that people are using to try to move things around at small scales are terribly inefficient, unbelievably inefficient. So the good news is the photovoltaic, somebody else engineered all that for us. So that's 10, 15, 20% efficient right there. The next thing to do is design the proper mechanical coupling of this actuator such that it couples well to the fluid. We are still trying to measure roughly speaking, the efficiency of that. We haven't done it yet. But what I can tell you is at least it has enough force at its disposal to easily move the things that we need it to move, to lift those panels, even if they have electronics on them and things like that. But in future talks, I would like to start to be able to give you an efficiency number. And this game shouldn't count unless you can do things at high efficiency. Because you don't just want one, you want a lot of these and you want them distributed, and so you want them to be harvesting energy effectively without everything heating up. But again, because we're stealing existing technologies, at least a lot of the pieces are already efficient.
Just a similar question. How does energy tolerance and stuff like that compare to biology?
Well, biology does everything fantastic, right? So, well, it does everything.
We did lots of things, right?
For example, we have better solar cells than biology, right? The best solar cells in biology are what, 5% or something like that, and ours are 20 or even more. So that there are places we can beat it. I'm sure at them, and then often, like when we're thinking about what is the elasticity of this thing we want in order to make a good swimmer, you can either do the calculation or you can just look at the biological equivalent and figure out what the spring constant was. That isn't answering your question because I think you have to decide exactly what part of the problem you're wanting to compare to. But we're wanting to compete.
How does this thing compare to a cilia?
Well, we're going to build it to look like a cilia, so it will do very well compared to a cilia. And again, our goal is to keep the performance numbers up to a reasonable scale. And I don't know what the biological efficiency, what fraction of how many calories are needed for a certain amount of force integrated to distance for that guy. So, but I will know in the future once we make something good enough to compare. We are just starting. Well, the ones that we're making here, as you saw, were all like 100 microns in size, so they're like too big, right? Yeah, they're a little bit too big. We could make them smaller. We don't, just because at this point we're lazy. But mostly they're extracellular at this point. We put them in tissue or what have you. But we're really interested in making the next. My vision of things in the future is there's going to be a cell phone or kind of a platform at each factor of 3 or each factor of 10 or something. So if you want to. There'll be the 100 micron one where you can get a full Moses chip with a brain and everything else. And there'll be a 10 micron where you can get a few transistors. And there'll be a 1 micron where maybe you just get an LED or something.
So the piece that you put into C elegans, how big was that? Into the worm?
Into the worm. That one is about 100 microns long.
Oh, I see.
But we didn't, I'll remind you, we didn't put that in there. We just put wires in there.
I see.
But we could have put that in there. We just haven't done it yet.
I thought it was inside. This one?
I just thought it was a picture of Earth when I see all these.
Oh.
Yeah, it was it was a monster.
I see everything very small.
So, is Vanderbilt still your biggest enemy?
Yeah,
I was thinking about the one that didn't work.
Yeah, the part of this that we still suck at in certain degrees is controlling adhesion forces and release layers and all that stuff. Like, we spend an enormous amount of our time figuring out how to get things off the surface in a controlled and good way, and also then not having them readhere. And in particular, making something where we can stick things together and then release them in a controlled way would be very powerful and nice. But as you know, those kinds of problems are very poorly understood. Problems of adhesion and de-adhesion in a complex environment. And we've done some work to study that in a different context, but that's a part of the problem that we haven't fully engaged yet, but would like to be able to grab things, which is easy, but also let them go, which is not.
Any more questions? If not, let's